Okay, so I'm doing a different video today. It's not going to be just some random problems or a past exam paper. We're going to have a look at the um, 2016 G495 Physics B, um, what's it called? The Advanced Notice article. That's the one. We're going to have a look at that. So this is the thing that you're given before the exam to have a look through. If you haven't looked through it yet, then I'll definitely advise you to do so, because the exam's in just over a month now. So it's good to have a look at it before and think of what particular questions can come up. You get a copy of it in the exam, so you don't need to remember anything. You just need to have a good understanding of what's present in the article so that you can answer questions on it in a little bit more detail than what you'd be expected of something that's tucked at you in the middle of the exam paper. So if we go to the first page, we see what the topic's about. So if we just have a little scan through, so we've got electricity for spacecraft, solar panels, nuclear power, and there's then a kind of little summary at the end which seems to have Faraday's principle over here, which means it's going to have a little bit of the electromagnetism stuff at the end as well. So if we look at the introduction, the electricity for spacecraft part, you see it talking about satellites and spacecraft, obviously. So the first thing that should crop up in your minds when you hear about spacecraft is the orbits. So centripetal force of an orbit and gravitational forces. So these are quite important things. Escape velocities, kinetic energies, potential energies, all of these should be ringing in your head as to the sort of questions it can ask you about. Because if we look just down here, two major considerations are mass and lifetime. You've got to think to yourself, well, why are these considerations? Well, obviously mass is going to make it a more difficult object to get into orbit. If it's a lot heavier, it's going to exert more energy to get up there. So in that sense, mass is going to play a big part. And obviously lifetime, depending on the mission of the object, will depend on how important the lifetime is. If you're just sending a probe up into space for a couple of days to monitor solar neutrinos or something like that, something that's not going to change over time, that you just want to put up and get a measurement, then lifetime's not important, and you're going to want to look at mass instead, keeping that down, keeping mass as low as possible and keeping lifetime as low as possible. But depending on the mission, each one's going to have a different weighting as to what you prefer. So it tells you a bit of random information. So battery is usually described as number of watt hours that they have per unit mass. So a watt hour is an energy, because you should know the equation. Power equals energy over time. Power times time equals energy. So watt times a unit of time, so whether that be seconds or what minutes or what hours, that's some form of energy. And it's saying watt energy per unit mass. So let's just get rid of this quickly. So the amount of mass that it has will basically cause the amount of energy that it's able to use to move to decrease. So they're using this almost not necessarily made up, but it doesn't have its own unit, but this sort of different type of quantity that will measure how well the batteries are performing. So how heavy are they, because you're interested in keeping the mass down, and then how much power do they produce, because you want to expand the lifetime. So let's move on to more this first section tends to just summarise what's going to be happening in the rest of the article. So it's talking about large distances, different electrical generation is required, so things like nuclear power, things like that. So And this is all going to come up, all this section at the top here is all going to come up in the rest of the article. It's just introducing the topic. So now we look to talk about solar cells. So it says that for in a solar system, probes, that solar panels are the most common generators of electricity. That's fairly obvious because you've got the sun that's very nearby, and it's it's producing energy that goes out into the solar system. And the further you get away from the sun, the less energy that's reaching you. So inside the sun, you can use it inside the solar system, like on the inner section, before Mars, I guess. You can use the sun's energy quite nicely, but after that, you've got to look at other things. And it gives you some numbers that are often quite important. Just make sure you get the numbers right when you're using them in the exam. Make sure you're using the right ones that are in the advanced notice article they give you. I think it can slightly be subjective change, so it doesn't expect you to just remember stuff. It can sometimes give you a slightly different value, so make sure you check what the advanced notice article actually says in the exam. And whatever the question it asks for you, because it says here a typical value for panels used in satellites in the Earth's orbit is 300 watts per kilogram, and it could be in the exam that you're looking at a slightly different one. In the exam papers it could be 250, 350, so it's just always important to make sure you're using the right values. It may sound stupid, but people still mess it up. So what does that mean? Typical value for panels used on satellites in the Earth's orbit is 300 watts per kilogram. So that means the mass of these batteries, the mass of the panels are dependent on what energy they have. So for every 300 watts that these produce, it weighs a kilogram. Now it says at the bottom here, after the picture, each array can produce a maximum of 2.8 kilowatts. So then you see here we've got the energy that they produce, like the maximum, and then we've got this other quantity at the top. So what it could ask, a very reasonable question, would be to work out the mass of the solar panel arrays. So you've got, even if you don't know an equation for this, you're not necessarily going to know it. So we've got this value, we'll call it power density. It doesn't matter what you call it, but we'll call this one at the top power density, and we'll give it symbol PD, and that equals 300 watts per kilogram. Then we've got this other value at the bottom, which is just normal power, and that equals 2.8 times 10 to the 3 watts. So then we see here the units that we've got on the other side. We've got a watts per kilogram at the top and just a normal watts at the bottom. So if we do this power divided by the power density, then we're going to get a unit in kilograms, and a unit in kilograms is obviously going to be a mass. So if we do our power over our power density, and what our power density actually is the power per mass. So we've got watts per kilogram, so we've got power over m, which means we're just going to get a mass come out at the end. Which means the mass of each of these arrays will be 2.8 times 10 to the 3 divided by 300. This thing's roughly 3 kilowatts at the top. So what you're basically doing is 3,000 divided by 300, so it's going to give 10 kilograms. If I do the calculations slightly wrong, it's because I'm doing them in my head, so just bear with me with that, and if you see a mistake then point it out in the comments so people don't get confused. But yeah, I'm as likely to make a stupid mistake as anyone else. So the next things it's given you is an orbit takes about 97 minutes, 36 of which the telescope's in the Earth's shadow, and the panels do not generate electricity during these periods. So a simple thing is just how many minutes is it out of the Earth's shadow? So how many producing minutes are there? So that's just obviously 97 minus 36, which gets us 61 minutes. and that means if it tells you that this value at the top here, 300 watts per kilogram, it could tell you that that's the amount, 300 watts per kilogram is 300 joules per second per kilogram. So it could ask you, okay, how much energy is the whole telescope producing in this time period? So we've got our, let's just get rid of some of this stuff on the side. So I'll rewrite down the values that we need. That's not going. There we go. So we want to look at the values that we need to pick out the important ones. So like I said, imagine the question's asking how much energy is produced in one orbit around one orbit of the Hubble telescope around the Earth. So one orbit is 97 minutes. It's got power producing time of 61 minutes, so we don't want that value, we want 61 minutes. We convert that into seconds, that's 3,660 seconds. And then we're doing, we're looking at this value, so the energy here is, now we don't even need to look at that, we can look at the one at the bottom because this is 2.8 kilowatts per array, so that's a total power of 5.6 kilowatts because there's two arrays, 5.6 kilowatts. Sorry about the awful handwriting, I do apologise, which is 5.6 joules per second. So the total power, so kilojoules per second, the total power will be 5,600 joules per second times the amount of time, and then that will give us the energy, so times 3,660, which will give us something very large, probably give about 1,600. I'll stick another 0 on there and take a guess at that. Maybe one more. But it'll give some large number, just sub it into a calculator, but that's the method to find it out in the end. Another question it can ask is, as I mentioned before, this is a satellite and we've got probes and things flying about in the galaxy, so orbital motion should come to your heads a lot. So it tells us 97 minutes, so 97 minutes is the time of the orbit. It could ask you from that, my spelling's just as bad as my handwriting, it could ask you from that, okay, we've got 97 minutes, using F equals mv squared over r, and F equals big M little m times by g over r squared. Using these two equations, find the using these two equations, find the time period of the orbit. No, not the time period, find the radius of the orbit using these two equations. So this might sound a bit daunting at first, but if they're forces, this is the centripetal force, so the force pushing outwards, and this is the gravitational force keeping it in. So you equate these two together and see what happens. You might have no idea, but we'll see what happens. mv squared over r equals g m over r squared. If it ever gives you two equations, stick them together, add them together, times them together, see what's happening and see what you can kind of get out of it. Let me see from this, I won't go through the whole calculation, but you just got to cancel the two m's and move the radius over to the other side. Then you've got v equals root gm over r. So then you've got this velocity, and you're thinking to yourself, okay, I've got a velocity, what do I do with this now? So let's see what we can do with this velocity. So if you remember as well, time period, or yeah, time period equals 2 pi r over velocity, because what you're basically doing is speed equals distance over time. Our speed is obviously our velocity. Our distance is 2 pi r because that's the circumference of the orbit, that's how far it's travelling. T equals big T, and S in this case equals V, and then you're just rearranging to get what big T is. And that's just the speed equals distance over time equation. So you see time period equals 2 pi r over V, and now we've got two equations we can quite nicely solve. So we've got 97 minutes of a time period, we'll sub that in at the end, and then we sub in our velocity into this equation here. So we've got time period equals 2 pi r over root gm over r. We'll rearrange it a little bit, and we've got root gm over r, that's the whole thing square rooted, equals 2 pi r over t. And then you can square both sides, so you've got gm over r equals 4 pi squared r squared over t squared, and then you want something in terms of r, so let's move all the r's over to one side and all the rest of it over to the other side. So we've got gm t squared over 4 pi squared equals r cubed, and then you've got a lovely equation for r. So if it gave you this question, it tell you what g would be in the constants at the back, 6.67 times 10 to the minus 11. It would give you the mass of the Earth, which is about 6 times 10 to the 24 kilograms. And you know what the time period is, 97 minutes, you just have to convert that into seconds, 97 times 60, and you know what pi is on your calculator, and you just do the cubed root of all that, and then you've found the radius. So that's the radius that Hubble's orbiting the Earth at. So that's just an example of a question that they could ask you, and then just a nice little solution of how to solve it. It's not a nice little solution, let me know, it makes sense to me, but if you haven't been able to make sense of it, then just ask and I'll try and provide a better description in either this, either in the comments or in another video. So there's no guarantee that that'll come up obviously, but it's a good example of what to start thinking about, because you'll need it for the G494 exam anyway, that sort of thing. The other important thing to note in this section is probably to do with the thing at the end, so the Earth shadow. For this reason, some of the electrical energy generated is stored on board in an onboard rechargeable battery, which can provide complete power for 7 hours. So why would it be 7 hours if we're only having 36 minutes in the Earth shadow? Well, obviously you want some extra kind of precaution period. If any of you say something to do with nighttime or clouds blocking out the sun, then you shouldn't be sat in the exam, quite frankly, because this thing's in space. So what you should be thinking of things like precautions. So if the solar panels fail, if there's a problem with the spacecraft, things like that. So just general sensible answers that will mean that they'll still be able to navigate it about for a short amount of time to get into a safe area if it's going to fall out of the sky, something like that, but nothing to do with nighttime or clouds, please. So that comes on to this thing that I mentioned earlier. So solar panels become less effective based on inverse square law. So inverse square law means that intensity is proportional to 1 over r squared. Until recently, the orbit of Mars, so Mars is an important one, was the greatest distance that solar panels had ever been used, but later developments have had them on probes into the outer solar system, such as the Rosetta probe to a distant comet. So the last bit's not important right now, we'll come to that in a second, but the Mars part is quite relevant, because a typical question it could ask would be, what's the intensity of light at Earth, given that I equals some constant over r squared, and what's the intensity at Mars. So you can work it out and then find out a ratio. So it will give you the radius of Mars, and you plug it into this equation using whatever constant they've given you here. So using whatever constant they give you, then you can find an intensity at a particular point. If they don't give you a constant, and they just want you to find a ratio, it doesn't matter either, because you can work out I Earth is proportional to 1 over r e squared. We can even say, for now we'll make up our own constant, we'll call it c, not to confuse with the I up there, and then I Mars equals c over rm squared, and then the ratio of the intensity would be just 1 divided by the other, so IE over IM equals rm squared over RE squared. So what that implies is that the ratio of intensity from Earth to Mars would be greater than 1, because the radius of Mars is greater than the radius of the Earth. So that's what you'd expect. And then if you plug in the values, you can work out the ratios that the intensity goes. I think Mars is about 1.5 astronomical units and Earth is 1 astronomical units. So if you sub that in, it doesn't matter what units you use as long as you're consistent. But if you sub that in, then you'll find that you've got something about the intensity being a factor of 2 or so larger on Earth than what it would be at Mars. But again, that question's not guaranteed to come up. It might come up in a different sense. It might not use the radius of Mars. It might not use the radius of the Earth. It could use the distance it's travelled, the distance the Rosetta comet had to travel. So that's why it's mentioned that one there. Obviously, it'll give you the value. You don't have to memorise them, but it's just important to think about what they could be using. And just for clarification, when I was talking about the radius of Earth and the radius of Mars earlier, I meant the orbital radius, not the actual radius of the planets, just in case that confused anyone. So what the radius would be is the distance that is travelled from the Sun. So in the case of the Rosetta probe, it wouldn't be the probe's radius itself, it would be the distance that probe's had to travel from the Sun, and you can use that to work out the intensity at that particular point. So if anyone's not aware, whilst I'm rubbing this out, the Rosetta mission was the European Space Agency mission that first landed a probe on the comet, or first had a soft landing of the probe on the comet. No one had managed to do that before, so it was quite impressive, and I think it happened last year. And yeah, they found small amounts of carbon molecules, and potentially it's backing up the theory that maybe life came from a comet rather than was on Earth when it started. So it's quite exciting stuff, and despite the probe lander basically dying and not working on the comet anymore, they still managed to get a lot of good data from it. So the next part is about nuclear power probes. So as soon as you hear the word nuclear, you should immediately think n equals n naught e to the minus lambda t. What's lambda? Lambda equals t. Lambda equals ln of 2 over t half. I think I've got that right. So that's the nuclear decay equation. So it's saying how the number of molecules or number of nuclei in a particular radioactive source decays over time. So that's just an important thing to keep in your mind, just like the centripetal and centrifugal and the gravitational force equations when you're doing this section. So we'll go through it line by line again. So first bit is telling us what we've learned, what we know before for longer lasting space missions, radioisotope thermoelectric generators. So whatever that means, it's an important, it's a particular type of way of producing electricity that can be used in the spacecraft, which we come on to a little bit later on. here. But again, we'll just go through the next bit first. So important to know that they're not nuclear reactors, so it's not asking you about fission or fusion in this section. It's the way that they decay, and then you can use that energy. It says there are other risks associated with such generators, especially during launch. So what can that be? Well, on launch, rockets have been known to blow up on launch. So one happened, well, it happens fairly regularly. There was one a few months ago, I think now, where it was supplies heading to the International Space Station, and I think 2 rockets that were being run by SpaceX had exploded. So it's a fairly regular thing that happens, and if you've got that with a nuclear source, so it's not fission or fusion, but you've still got nuclear isotopes in there, then that can explode and spread about over the nearby land, and then you've got problems because it can affect farming and the soil, and it can cause health problems and things like that. So if it asks you about what these risks could potentially be, you say explosions can happen on launches, and this can lead to a fallout in the area which can affect farming and human and animal health. Next section, kinetic energy. So these are the energies of the alpha particles. So kinetic energy of an alpha particle. So I can't remember exactly what the mass of an alpha particle is. I think it's something particularly large, because a proton's about 1 GeV. So it could ask you if this is relativistic. So if you remember, if you've got E kinetic plus E rest over E rest, that equals gamma. So that's total energy over rest energy. So you can use that to work out the I think it's called the Lorentz factor. So gamma, how close something's basically going to the speed of light. So if it asks you, is this alpha particle travelling relativistically, then it wouldn't be, because the rest energy's order of something GeV, we'll say it's 5 GeV for now. So you'll be getting something 0.0055 for the kinetic energy plus 5, all divided by 5, so it'll basically be equal to 1. So you know it's not relativistic, so it's not travelling near the speed of light. So that's just a simple question it could ask you about that. It can obviously ask you other stuff with the kinetic energy. It could give you its mass and ask you how fast it's going, what its momentum is, things like that, and you should be able to use the typical equations to work that out. But the most important part is probably when we get to the half-life, so being 87.7 years. So like it says, no danger of the energy running out, because it's a very long time, and space missions don't tend to last that long. I think Voyager was launched about 25 to 30 years ago, and that's managed to get out of the solar system. So you can travel a long way in 90 years, and it's not something to particularly be worried about. But what we do know with half-life is T half equals ln 2 over gamma, so, not gamma, lambda, so lambda equals ln 2, natural log of 2 over T half. So then you can work out what the lambda, the decay constant, is. Decay constant. And you have to convert T half into seconds, which will mean, the way I always convert into seconds is just simply, okay, I've got 87.5 years or whatever it is, how many days are in a year? Okay, we've got times 365, how many hours are in a day times 24, how many minutes in an hour times 60, how many seconds in a minute times 60 again. And you can just plug that into your calculator and get out whatever comes at the end. Then you're able to work out what the decay constant is. So once you've found the decay constant, lambda, then we can use this decay constant in the most important nuclear equation that you know, n equals n0 e to the minus lambda t. And it could ask you, okay, initially it's had, we've had, I don't know, 10,000 isotopes or 10,000 nuclei, and how many are we going to have after 40 years, say. And you just have to sub in n equals 10,000. It could be a lot more than that. It's probably quite likely to be a lot more than that. I'm just using that as an example. You just sub in 10,000 there, whatever your lambda is, and then your time, making sure that that time is converted into seconds again. So 40 times 365 times 24 times 60 times 60. Okay? So yeah, then you can work out how many are left over. You've also got to remember things like activity. So it could ask as well what the activity is after 40 years. So you just carry out that same thing, work out your value of n, and then you'd use activity equals lambda n. I think that's the right equation. I haven't used it since A level. It's a bit of a pointless one, if I'm honest. But it could ask you, find out the activity, and that's measured in becquerels. So that almost covers this section. The other thing it says that we almost missed out was voltage is then generated using a thermocouple. So a thermocouple is just a way of generating electricity due to a temperature gradient. So you have some form of section where the reaction's taking place. So a sort of box like this, and you have some sort of thing that then goes out and gives power to the satellite, and you're having the decaying source here, and it will be decaying and firing out alpha particles. They're all ending up at this end and hitting things and making it really hot. So you've got heat come up at this side, whilst it's relatively cold on this side because nothing's really moving except the things going across this way. So you've got a temperature gradient on this side, so you've got big T and a little t on the other side, and that temperature gradient is, with some clever electronics and physics, is able to produce electricity due to the temperature gradient. So you shouldn't need to know that in too much detail. It'll tell you stuff about it if you need to. It could give you an equation that works out to use the kinetic energy or something like that. But I think that probably the furthest it'll go will be some form of the number of alpha particles, and asking you to work out the temperature at one end, which would be E equals some constant. You sometimes use 3/2, but it shouldn't matter too much. But Ng equals nkt, so it's the kinetic energy of the alpha particles. So the total number of alpha particles times their kinetic energy equals kt times by n again. So your kinetic energy will relate to kt in some way, and then you'll be able to work out the temperature at one side. But it'll pin you in the right direction if that's what you need to use. What else is there? That should be about it. It could tell you the voltage that it's producing, and then telling you to work out the current through it if it's given a resistance of the components. So that'll just be V equals IR. So it does open up to the electronics part of the module, but very kind of loosely, more so in the the next section of the paper will ask about this. This one will tend to stick to nuclear physics, a little bit of mechanics, like the gamma factor and the kinetic energy. It hints it towards mechanics, and then after that you could maybe have something to do with temperature in there as well. We'll go on to the next section. If you've got any questions about that one, then don't be afraid to ask. So the next section is probably the weirdest one. It's a bit vague, but it says for the last 2 decades, studies have been made possibility of generating voltages using Faraday's principle of electromagnetic induction. So, what's Faraday's principle of electromagnetic induction? So this is EMF, so voltage equals d n phi by dt. So that's the rate and change of flux linkage, if I've got the right one. And also know that phi equals BA, so magnetic field times the area of the coils. So that's a couple of equations that could come up a lot. It describes the system that it's involved in. So you've got a long electrically conducting cable. So electrically conducting electric circuits, that can come into this quite nicely. It's given it a length. It could ask you to work the conductance or the resistance for it, given the conductivity or something like that. So resistivity equals RA over L. Conductivity is the inverse. So conductivity equals 1 over rho. So if you can use things like that, then you can find out the conductance and the resistance. And if it gives you an area of this cable, it's giving you the length here in this question, so that sort of hints that it could ask for something like conductance, conductivity, resistance, resistivity, and then go into the V equals IR type area. And what it's saying is the way it's generating this electricity is these cables that are going down into the atmosphere, cutting with the atmosphere, and then generating electricity by conducting wire cutting through a magnetic field. But yeah, so cutting through an electric field, and then the voltage is generated. So the thing we'll look at first is actually this section at the end. So this is not a case of generating electricity from nothing, but the method is relatively cheap and simple. So it could ask a sort of very varying question in the exam of what are the advantages and disadvantages of this thing. So you'll say, okay, it's cheap, it's simple, you're creating electricity without having to send up massive solar panels attached to things, questions like that, answers like that. And the disadvantages would be, well, this wouldn't be very good for the Rosetta mission we had earlier, because that's travelling out to a comet somewhere that doesn't have an atmosphere, so this can only be things going around Earth's orbit. It wouldn't work for geostationary satellites, because they're going to be moving with the Earth's orbit, so they're not going to be cutting the field lines constantly. Low polar orbit ones, the ones that are going around a lot quicker, like the ISS, would be able to use this. It's also got the disadvantage potentially of it having to, like I said, stay a lot lower. It's not going to be used for long travels, things like that. So things that will come up with staying fixed and being a lot more restrictive than something like solar panels or nuclear power would. So it's telling us about a bit of the information here, which is just generally a few key numbers. So how long it is, 20 kilometers, and the voltage it's generated so far, 3.5 kilometers. It could ask you to compare this to the values that you had from earlier. So how does that compare to the Hubble telescope, which, if we go back up and look at it, it was 2.8 kilowatts. Well, that's per array. Each array can produce a maximum of 2.8 kilowatts. So here we've got 3.5 kilovolts being produced, of voltage being produced. So you can relate voltage and energy to each other. I can't remember the exact equation now, but there is one in the formula booklet. But you can convert that into some sort of power. P equals VI, for example, if it gives you the current. And yeah, like I said, you can compare the two and see which one seems to be better. It could also have questions about efficiency, so how much it's losing as it's travelling up to the 20 kilometres up to the top, because wires lose electricity over time. So if it tells you something about efficiency, then you can use that to compare the powers as well. So there's lots of questions that they can ask you about it. Things to do with ions and stuff in this section. I'm not 100% sure what they can ask you about it, but they'll make it more clear in the exam. It'll be to do with things like Faraday's law, things like efficiencies, things like powers, voltages, distances, resistivities, conductivities. So this is where you want to know the electromagnetism type stuff and electric circuits. Yeah, so it could ask from a previous part in the question, if you've worked out the radius of the Hubble telescope from Earth, it could ask you how could this be possible for the Hubble telescope, given that the atmosphere is 80 kilometres or whatever it is, 80 kilometres high, and you've worked out the radius of the Hubble telescope. You can subtract off the actual radius of the Earth, and then if that's within 80 kilometres, then you know that you can, or if that's within 100 kilometres, because you've got the 20 kilometre line going down to it, if that's within that region, then it would be possible for it. If it's not within that region, then it's not possible. So you just got to get thinking about these sorts of things. Have a little quick summary. So I don't know why that's done that. Okay. So first section is just outlining everything they want to take a look at. So it outlines the 3 sections. We've got this one, which goes all the way down. So we've got to know a bit of solar power, which means inverse square law. We've got this sort of power per mass. It tells us about orbit times. So orbit time, which means we can work out an orbit radius. This means we need to know orbital forces. And then, yeah, like it gets to here, inverse square law is this section, and to do with light intensity, and working out ratios and things like that. So that'll generally be what the first section is. And this one's to do with nuclear power. So nuclear power. So we've got n equals n naught e to the minus lambda t. So we want to be able to relate t half ln 2 over lambda. And you want to probably know activity equals lambda n. And like I said, be aware that it could ask you things to do with electricity and electric circuits, basically across all of these 3 sections, because that's what in the end it's producing. Well, this one's mainly nuclear. And then this one is electromag. So you've got Faraday's law, which is important to remember, dn phi by dt equals epsilon. So your category of magnetic field, so phi equals BA. And also, like I said, I think we're giving you a length, resistivity could come up, so rho equals RA over L, and that relates to conductivity by 1 over rho equals 1 over sigma, because it's also giving you a voltage, which would imply resistance is probably going to come up somewhere. If it gives you the resistivity and the area, for example, and tells you to work out the current flowing through it, then you have to find the resistance first and then use V equals IR to find the current. So it all link into the circuits area, but the three main topics for each individual part is electromagnetism, nuclear physics, and I've forgotten what the first section was. Yeah, solar power. And again, like I said with the airy-fairy question at the end of this section last time, advantages and disadvantages, so know what the good points or the bad points of either of these are. So which ones are good for long travel, which ones are good for short travel, and this one at the end is kind of good for orbits in a limited sense. You don't have to keep supplying power and batteries to it, but it's not very flexible in that sense. So if this has helped in any way, then that's good. That's what I do it for. If you've got any questions about it, then don't be afraid to ask. Contact me. Leave a question in the comments below, or just have a little look through what I've said again. I can't guarantee that any of these questions I've said are going to come up. I can't guarantee that any of this is going to help, because I don't know what the exam's going to be, but just read through it lots. Set up some questions between you and a group of friends, so each come up with a question about it to ask each other, share that, mark it amongst each other, because being well prepared for the section C part, can basically guarantee you, I think it's about 20% of the exam, isn't it? So, something like that, 20-25% of the exam, and they're marks that you probably can't afford to throw away. There is also example questions from, I think, Matthew Arnold School online on their website. I'll try and put a link to them below in the description, and it's just got a mini paper of about 20 to 30 questions on this exact article, and then a mark scheme to go with it, so that's good use for a bit of practice as well, because none of the other section C parts that you'll see in previous papers will be any use to you, because they're something completely different. So hopefully that's been of use, and let me know if so, and let me know if not, and I'll hopefully put some more videos up soon.